Hello. Thank you so much for tuning in. I'm Jedediah Williams, coming to you pre-recorded from Nantucket High School. I originally planned this as a session for NCTM Atlanta back in September. And although we won't get to have the same discussions that we would have in Atlanta, I invite you to reach out over Twitter or email. Because the format is different, it wouldn't be the same style as if we were in person. I hope that you will use the pause and rewind if you can do that. All of the slides, along with additional resources, are available at the URL shown at the bottom left here, jedediah.com/NCTM2021. Let's get started. My understanding is that I'll be able to schedule a roundtable, but only once the conference starts. It's still October right now, so I can't schedule it, but I anticipate scheduling it for November 18th at 5 p.m. Eastern time. If that changes or if there's an update, I'll update the website. So I hope that you'll join me there. I very much look forward to seeing you, and check the website to double check the time. Data science and consequences in mathematical modeling. I'm Jed. I'm from Nantucket, Massachusetts, 30 miles off Cape Cod. I'm from Nantucket. I was born here. I grew up here. I went to Nantucket High School. I started teaching the week before I graduated college because there was an emergency leave. Everybody's fine. Don't worry. That was around 2006. I taught physics and astronomy for a few years. I left for a little while and studied robotics, came right back, and now teaching computer science and math, along with physics sometimes. I always wanted to be a teacher. I love it. Data science. The goal for this presentation is to present a data science process as a tool for doing data science, teaching data science, and critically analyzing data science applications. There's just so many things to talk about and talk through, and I'm not going to attempt to touch upon most of the things that I'm really just aching to talk about regarding data science. Instead, I'm going to talk about this basic approach that I take to introduce ideas of data science into my classroom. The big idea is to frame modeling with data as data science, so that as the models my students learn and work with increase in complexity, from linear models to polynomial or sinusoidal models, exponential or maybe logistic, even possibly tree-like branching computational models, they'll have a consistent workflow for modeling with data, a workflow they use for the simplest models as well as the more sophisticated ones. This idea of critically analyzing data science applications, I think that gets left out a lot of the time, right? The way that I look at it is that the word mathematics can mean a lot of different things. It could mean the collection of knowledge surrounding numbers and the operations on those numbers. But we also often use the word math to refer to the class, right? Or the discipline. I love math. I hate math. I've always been pretty good at math. I'm not good at math. When we hear that, we know students really aren't talking about the body of knowledge of numbers and operations. They're talking about the class, right? They're talking about their experience in the class called mathematics. We can use math to talk about the word math to describe the processes surrounding the acts of exploring, learning, teaching, applying mathematics. So when we say that we are teachers of mathematics, I often wonder which mathematics we're talking about. Data science is an enormously broad term. It evolved from multiple directions, largely from business analytics and data mining. With the rise of big data, we saw more people working on problems of leveraging that data to discover insights, really to maximize profits, right? But lumped in with that, we often hear about machine learning and AI applications, neural networks, whatever those are, get thrown at everything these days. Computer vision and natural language processing are two applications that are frequently cited as big success stories. Their accuracy has really gone up quickly in the last decade. Not necessarily everyone involved with data is a data scientist. There are many people who are data scientists whose daily jobs are not alike. In fact, the more specific we get with any definition, the more people we exclude from data science. There are so many roles related to data science, especially as the applications and processes around data science have grown. At gigantic corporations, you are likely to see more and more specialization in those roles. And a lot of these overlap, but a lot of them don't. I'm a fan of the book Doing Data Science by Rachel Shute and Kathy O'Neill. They have an excellent description of how challenging it is to define data science. And they propose this thought experiment, teaching data science. How would you design a data science textbook? It's not a well-defined body of knowledge, and there's no canonical corpus. It's popularized and celebrated in the press and media, but there's no authority to push back on erroneous or outrageous accounts. There's a lot of overlap with various other subjects as well. It could become redundant with a machine learning textbook, for example. Joel Grus writes in his book, Data Science from Scratch, in fact, some data scientists are, for all practical purposes, statisticians, while others are pretty much indistinguishable from software engineers. Some are machine learning experts, while others couldn't machine learn their way out of kindergarten. Oh, Joel. In short, pretty much no matter how you define data science, you'll find practitioners for whom the definition is totally, absolutely wrong. If you like Venn diagrams, you'll enjoy image searches of data science. There's so much overlap. And there's a limit to how productive the conversation is around what data science is, right? So if we can't define it, right, I'm kind of struggling right now to define it. Where can we look to maybe get a sense of it? We can get a sense of what schools think data science is by looking at academic programs. This is a set of courses from UC Berkeley's new data science master's degree. We can see courses like Introduction to Data Science Programming, Research Design and Applications for Data and Analysis, Stats for Data Science, Behind the Data, Humans and Values. That sounds like a great course. Deep Learning, Data Engineering, Applied Machine Learning, Data Visualization. This gives us some sense of what at least UC Berkeley thinks data science is about. We can get a sense of what industries think data science is by reading job postings. So I did a Google search just this morning for data science jobs. This was the very first one that came up on Indeed.com. You can take a look at the work experience required for this job. It involves a lot of popular platforms designed specifically for doing data science, which can be pretty confusing for someone wondering about or wanting to get into the field of data science. You know, a lot of the requirements for the job of doing data science is a familiarity with tools specifically designed for doing data science, right? That can be a little bit confusing. We can get a sense of what data science in industry actually is by hearing about the tools people report using. Python, very popular programming language since around 2017, has been consistently reported to be the most commonly used software tool in data science and machine learning. And I think that has grown even more since then. I personally do most of my data work in Jupyter Notebooks using Python. My students, however, I really want them to be familiar with spreadsheets. Spreadsheets are so powerful. I love them. About 12 years ago, I did a lot of work just in spreadsheets. I spent a few years working in MATLAB, and now I work in Python, but especially for simple models, I think we should start our students off with spreadsheets. love them. Okay. I think one of the wonderful things about data science is that it seems to be an innate human desire, right, to look for, observe, and infer from patterns, even when we're often wrong about it, right? We are naturally scientists. This graph, more than 1,000 years old, was described by Howard Funkhauser as possibly the earliest graphical display. Is just so cool. What an interesting piece of history. Of course, one of the earliest known graphical displays would be about astronomy. I want to also point, though, to the Kipu, for example. So this is this string with lots of other strings tied to it, used in Andean South America for at least 1,000 years. We don't know how long it's been in use for. It could be thousands of years. The string has colors. It has these knots. The string can vary in length. It's really a multi-dimensional database. But what I find really most fascinating about the Kipu is that it's simultaneously a visualization of the data in its database, right? It's similar to a spreadsheet. If you do conditional formatting, like color formatting in the spreadsheet, and you get that visualization from your data, the Kipu really achieves that. They're beautiful. If you have time, check out this link on the right. My understanding is that it's only recently in 2017 that it was discovered that some Kipu correspond to census data from Inca cities. That's just so cool. But it's a visualization at the same time. It's a database. Switch to modern times. Amazing things are happening with data and modeling. Elon Musk says we're only 2 years from being able to nap in self-driving cars. That is, we will be able to just tell our car where we want to go, and then fall asleep and wake up, and we'll be there. He said that, however, back in 2017, and then he said it again in 2018, and then he said it again in 2019. And I really, really do not recommend that you fall asleep in your car. You will be harmed or worse. This begs the bigger question, why is Elon so sleepy? This is where I need a live audience. I'm giving you time to laugh. Okay. Despite a lot of the hype, there are actually great things happening thanks to data tech. Here are some examples from Fast AI's talk. Deep learning is overhyped. Fast AI is this resource put together by Jeremy Howard and Rachel Thomas. They offer classes that allow people to learn some basic Python skills or programming skills to get up and running with deep learning projects very quickly. And they highlight some of the very cool projects from people out there doing really great work to help other people using data-related technologies. Sarah Hooker and Rainforest Connection creating tech to detect chainsaw sounds to address illegal cutting of rainforests. Elena Harley, tumor normal sequencing for dramatically improving classification accuracy of tumor tissue. Data-powered algorithms for image labeling to support visually impaired. So someone can hold up a cell phone, it will use deep learning trained algorithms to label what's in the view and speak it to the person. Just really cool, really powerful technology that's making the world a better place. So how do I introduce data science to my students? I use what we could call a data science process. This is not an original idea. It's been around for decades, longer even than the sort of modern definitions of data science. The big idea, the rough summary of this process is you get the data, you clean it up, you inspect it, you model it, and then you share your work. And this acts as a framework for students to create data science projects, but it also is useful for teachers to frame those projects or scaffold those projects. And we'll see later on how it's also useful for critically analyzing data science projects. Again, this is not an original idea. There are several examples of similar conceptions, several basically identical conceptions. I encourage you to go check those out. Some of them are different and have different stages. We could, for example, call the first stage of data something else. We could call the explore stage visualize. Right? This is one conception of this process. Okay, I want to add some level of detail to each of these stages while reiterating that data science is gigantic. So we can only add so much before we start narrowing the scope of the descriptions to the point that they become less accurate. I'm going to break each of the stages into really two steps. So the first stage, data, has these two steps of design and acquire. One of the first things we might do as a data scientist is to take a problem and translate it into a data problem. So we might work for a company where they have some issue that they want to resolve, some problem they want to solve, probably some profit they want to maximize, right? And so we can take their problem and translate it into a data problem that we can use data science to find an answer to. The design stage could involve experimental design or survey design. If you're accumulating a huge amount of data, you might need a data center, right? So that could involve some database architecture or some work with real architects to build the buildings where these data centers are going to be stored. And then the step of acquiring the data, actually do the experiment, send out the survey. A lot of folks working with data are often just handed that data, right? We might be able to download a data set, or someone might just send us a spreadsheet of the data, or we could use some scripting to web scrape. We might grab text from a website or look for videos or images on social media. The next stage, pre-process, possibly the step that students and maybe we are least familiar with. However, this is a hugely important step in doing data science. There are many claims that this is where data scientists spend 80, 90%, depending on which data scientist you're talking to. I watched an interview recently with Neha Kathari of LinkedIn.com. She is a senior data scientist there, and she stated that 80% of the time, approximately, is really just spent getting the data into some usable format, getting the data that you want to use to create some model. Preparing the data, that might involve labeling the data. So you can imagine a huge image database where you want to label all the images that have cats or all the images that have dogs or something like that. The labeling used to be done largely by graduate students. Now there are several companies, most famously Amazon's Mechanical Turk, which offers services where people can earn small amounts of money at a time by doing this labeling for companies. Splitting the data into training and testing sets. This is a very powerful idea for model validation, and we're going to see an example of that in one of our examples. Okay, this is not a complete list, but these are several of the things you might do in the pre-process stage. In the explore stage, probably, at least for my high school students, the thing they're going to do most frequently when they explore data is visualize it. They're going to plot it. They're going to take some of their variables and create a graph. They might find and compare features. When I say features, I'm talking about a variable, like a particular column in a spreadsheet. While they're exploring that data, they might start thinking about what models are most appropriate for this type of data. They're going to inspect the data. They might look at descriptive statistics. They might find new features by combining variables into new features. and they might compare features against each other. The stage of modeling, this is, you know, the big picture stage. We have our data. We want to come up with a model that fits that data, so maybe we can make predictions about future data points, or classify an image or a video. Is this email spam or not? Classic classification problem. So my students, we work with models like linear models, polynomial sinusoidal models. Not many of them, but sometimes I'll get a student who's really into this and wants to do something more advanced. A very important stage in modeling is validation of our model. This is something else that we'll see an example of. And the last stage, communicate. So you have a model, it is successful at something, you need to tell somebody about that, or maybe report back to your boss, you know, my model is successful at predicting this thing 99.8% of the time. It could be in the form of a report or presentation, technical documentation. It could be information that's used to inform a policy decision. There are all sorts of things that you might do once you have a working model. Okay, here's the rough summary here. When I'm using this process with students over the course of several projects, typically using more and more sophisticated models, I'm trying to get them to abstract their data applications into this data science process. So with one project, they might download the data, normalize and split it into training and testing sets, plot the data so that they can familiarize with it, consider what models would be most appropriate for that data. Then they'll try different models and they'll assess the model performance against their testing set. And then their communication step might be to actually implement that model in some sort of, I don't know, product, or it could be something else, right? Instead, we might start a different project by translating that problem into a data problem. We might design a survey. That survey data is probably going to be very messy. So we need to clean it, organize it, transform it into usable tables. Maybe split that data again into training and testing sets. We might inspect that data by using exploratory data analysis techniques like just plotting, looking at descriptive statistics. Try multiple models again, validate, and this time maybe we'll write a report. But whatever the project is that we're doing, I really am encouraging, as we go through this iterative process of more and more sophisticated models, I want my students to project onto this process so that so that they can have some sense of where they are in this process. Here's an example. So the given problem is, how high do bouncy balls bounce? The first step we're going to take is to translate that into a data problem. Given a particular bouncy ball dropped from rest at a height of hi on a consistent surface, what is the predicted peak height HP of the first bounce? This is much more a data problem. Collecting that data, most of my students will work in groups, and every group will have, you know, access to a cell phone which has slow motion video capture, just incredible technology right in their pockets. So they will do lots of trials and record each trial in a slow-mo video. That video they record, that's the data collected. In the next step of pre-processing, here that involves parsing the video data into a table. For my students, I really try to emphasize the difference between the data which is collected, in this case, the video, and the pre-processed data, in this case, the table in a spreadsheet that's ready to be explored. While we might be tempted to view this step of creating the table as being part of the data collection, the parsing of collected data into usable tables is a separate thing from experimental design and data collection. And segmenting the stages in this way is really analogous to how modern data science works. For example, raw vision data might be labeled by graduate students or through services like Amazon's Mechanical Turk. But those are two different processes. One step of collecting the data, another step of cleaning up the data or getting it ready to be used in exploration or modeling. So once the data is in tables, they can plot it, explore it. Again, with my students, this explore step is pretty much 100% of the time going to be a graph, a plot. So they plot it, they explore it, they look at it and wow, it looks linear. If you are looking for some sort of lab, some hands-on activity for your students surrounding linear functions, bouncy ball height is a great one. So they decide, okay, it's a linear, it looks linear anyway, so I'll come up with a linear model to fit this data. They come up with this linear model that fits this data, but importantly can be used to make predictions about future data points. So to validate our models, in this particular experiment, we do 3 different validations. One is an interpolated drop. So on this plot, I can see that these students dropped from heights roughly 5 centimeters to 1 meter. So we might then make a prediction about what about at 42 centimeters? What should the bounce height be? So they can use their model to make that prediction and then do the experiment to see how close their prediction is to the result. Another stage in validation is an extrapolated test of the model. So this one only goes up to 1 meter. Does this model still work for 1.5 meters? Often with our bouncy ball experiments, it does. And then another validation stage that we use for this particular experiment is an extreme extrapolation. We go out to our stairwell and we drop it from the very top floor all the way down to the basement floor. And it turns out we find that our linear model does not predict the bounce height very accurately for this large drop height. If we were live right now, I would ask, do you think our model under or overestimates the bounce height for large drops? Maybe hit me up in an email. Let me know what you think. If you're really curious, ask a physicist. They'll probably be able to tell you what's happening with the bouncy ball, the deformation of bouncy balls when they hit the ground. The last step here is the communication step. So we invite students to communicate in a number of ways. They could do a video, they could create a podcast about it, but they always choose a lab report. They just are super comfortable with that from science class. With a more advanced project, this stage could include making some policy decisions. For example, several of our school decisions have been made by taking polls, collecting data, and then at the last stage, making a policy decision. So that's really a data science project. Let's take a look at another example. I live on an island, so I always have somebody in the class who likes to fish. I don't go fishing myself, so I'll pick a student. What time should Zach go casting for blues on Saturday? I have no idea, but I'm told that the best time to go fishing for bluefish is at high tide. I believe it. So we translate this into a data problem. Using the tide data from the NOAA Brant Point Station and TKM3, we have a NOAA station here on island. When do we predict high tide will be on Saturday? And so this data is available online, so the students can just download it. They don't have to actually do an experiment to gather this data. So once they have the data, the pre-processing involves just copying this data over into a usable table in a spreadsheet. There are also often some corrupt rows, like there might be a time period where there wasn't a water level recorded, so we have to throw out those blank rows. An important step we also take in this project is to split the data into training and testing sets. So we'll use a random number to decide which row gets put into the training set and which gets put into the testing set. We randomly take 70% for the training set and leave 30% over for the testing set. We'll set that aside and we'll train our model only on the training data. And then as a last step to validate our model, we'll test it against the testing set. So we split those into our two different sets, our training set and our testing set. We visualized the training data. Remember, our testing data is separated. We don't actually see it yet. Students look at this and they say, oh, this looks a lot like the sinusoids we just studied last week, right? Or hopefully they say that. Then they model it. So they model it with a best fit sine or cosine. Then to validate their model, they assess it against the test data. I think it's pretty common to look at model metrics like residuals, mean squared error, R-squared values. Those metrics can be more meaningful when they're assessed against new data or test data, rather than the data that the model was built with. If you assess your model against the same data that you used to create it, then you increase the risk of some pitfalls like overfitting your model. This idea of splitting the data into training and testing sets is just such a powerful and fundamental idea in model validation that if I had to pick just one data science-y thing to focus on with my students, I think it would be splitting data into training and testing sets for model validation. Okay, the wrap up for this project is some sort of communication. Here is a report. And Andrew, I love you, but you swapped your X and Y axes on this plot. Okay, I'm not going to go into a full explanation of this next example, but I wanted to give an example of a project we do that is different from those first two projects we looked at. This one is a computer vision project where we need to create a model that can classify 4 types of fruit from images. So I give you an image and your model should process it and give an output apple or blueberry to hopefully accurately classify the fruit that is in the image. There is a link down at the bottom of this slide that you can follow and a link to it on the website. It brings you to a Google Colab project in Python, which you can run. It walks you through the stages of the data science process and even includes a model that's capable of accurately predicting the fruit from an image roughly 70% of the time. That's not that great. So even if you don't have programming experience, you can still walk through and just hit play in the Google Colab and see what the output is. And you might be able to hack at it a bit and fix my model so it achieves something closer to 70% accuracy. What you'll see if you run that collab is that we look at the range of red, green, and blue color values for each of the categories of fruit. So you can try to look at the distribution of red, green, and blue in apples, and maybe think of a way you could distinguish apples from bananas using that red, green, blue data. Distinguish that from blueberries, distinguish that from oranges. If you take a look at the collab, you'll see where that happens in the code. And even if you don't have a lot of programming experience, some of it will look confusing, but you'll be able to find the place where you can just hack at it and maybe change some things to hopefully get a better result than mine. Okay, consequences of mathematical modeling. The lesson here is that it's rare for machine learning applications to not be about people. This is from a book called Fairness in Machine Learning. Of course, when companies are deploying products, they have some effect on the society into which they deploy these products, especially when those products use data from that society into which they're deployed. These are some talks that you should watch by people who know a lot more about this than I do. Rachel Thomas from Fast AI has a great video and series really on ethics and data science. Race After Technology by Ruha Benjamin. It's a wonderful book. You can watch videos, talks from her about that. Cathy O'Neil, cannot say enough about how fantastic Cathy O'Neil is. Many of you will be familiar with her book, Weapons of Math Destruction. Joy Buolamwini, How I'm Fighting Bias in Algorithms, has done fantastic work. I highly suggest you watch these videos from all of these incredible data scientists, and maybe even just stop this video right now. No, don't go. I'm going to walk through the data science process and talk about how bias and harm can be introduced at every stage of the process. So data is one of the most infamous places where bias can be introduced into a data science project. Sampling bias, again, Joy Buolamwini, who has done work with Timnit Gebru, formerly of Google, on gender shades. You might have also seen her work about actionable auditing, really making an impact on minimizing some of the harms done by large companies by really just holding them accountable for that harm. Sampling bias is one of the main ways that bias can enter into a data science project, but also bias of the time period. There's this question of, should data sets have an expiration date? So if I'm maybe using some data to make a decision about education policy, I probably don't want to use data from a century ago, right? Data has an expiration date. The data from a century ago is going to reflect the values of that time. It might, using that data could take those values and incorporate them into our model in potentially harmful ways. Privacy and consent, huge issues with data science projects. I think when a lot of people first started joining social networks in the early 2000s, there were so many data technologies that did not yet exist. So when people were just pouring their images onto Facebook, for example, there really was no understanding that Facebook would have those images almost 20 years later and have the ability to use those images on new technologies that we just weren't aware would exist at the time. Inadvertent consent, when we are just clicking OK on those user agreements, are we giving away our privacy? Environmental impact. I'm hearing more and more about this, where I don't think I heard a lot about it previously, but gigantic data centers have a huge environmental impact. They have a huge carbon footprint. If you have clusters and clusters, right, of data storage along with data processing hardware, you're going to be using a lot of energy. There are also issues with just poorly designed data collection. We recently here at NHS had to fill out a form, and in the form, you had to enter your name into a text box. That text box was programmed to only accept alpha characters. It would not accept, for example, hyphens. So some of my colleagues weren't able to enter their legal names into this text box because they had hyphenated last names. I see something similar with my students. So if there's an assumption about cultural conventions of naming, right, where you assume that students all have a first name, middle name, last name, well, we have a lot of students who don't conform to that convention. I'm thinking particularly of my students from El Salvador, who when they get here and they go to the guidance office and there's some counselor helping them to enter their name into our student database, they have to figure out a way to get their name to fit into the format first name, middle name, last name. So I have many students for whom when I'm taking attendance in the morning and I see their name in our student database, it does not match the name that they identify with. That's harm. Okay, so I want to say that one of the big misconceptions about algorithmic bias is that it's solely due to biased data. Of course, it can be due to biased data, but bias and more generally harm can be introduced at any one of the stages in this data science process. In the pre-process step, one of the biggest issues that I'm aware of right now is labor exploitation. So you can click a lot of the links next to these if you want to read more stories giving particular examples of this. So labor exploitation for labeling, for example, leveraging the gig work environment to get labor without offering benefits, outsourcing labeling to other countries where maybe there's less oversight over working conditions, trauma experienced by labelers. Imagine someone working for a social media company and this person is responsible for finding and labeling and addressing maybe pornography or violent imagery. There are all sorts of horrible images that this person might see in their day-to-day job every day. So we have to ask, what toll does it take when someone is seeing this horrible, traumatic imagery every single day they go to work? Another issue is just incorrect labels. So inaccuracies from non-experts labeling sensitive data. So some companies might be outsourcing the labeling of medical data, sending sensitive medical data to other countries, possibly. There are, for example, sending it to India. There are some cases, user cases that Rachel Thomas talks about with this. Sending over sensitive medical data and having people who are maybe not that invested because they're getting paid so little to do this work, and they're just not experts, they're not medical experts, but they're the ones labeling this medical data that might then be later down the pipeline fed into a model. So if we have poorly labeled data and we're using that to train a model, we might be causing arbitrary harm that's unpredictable because we don't have well-labeled data. There can also be basic errors. Watch the hilarious Matt Parker on his talk about spreadsheets and just how many errors there are in any given spreadsheet. In the stage of explore, right, seemingly benign, you're just looking at data, but I think math teachers in particular are aware of how bad data visualization can be. This stage is critical for developing our sense of the data, and bad data visualizations are misleading. They can distract from real issues. There's also bias in choice about features. Again, when I say features, I'm talking about particular variables. If I have a huge data set and I'm at this stage making decisions about what variables will be included in my model, well, that's a choice where I'm putting my internal bias into the modeling process at this stage through those choices. Unfortunately, another way that harm can be done is just straight up manipulating the data, and you can read about the ShotSpotter story through this link. At the stage of modeling, we can introduce bias through model choice. This paper, Same Data, Different Conclusions, talks about giving a large number of research groups the exact same data and letting them model that data and make inferences from it. And it talks about just the wide range, even contradictory conclusions that people make, that these research groups make from the exact same data set. Really solid evidence that while data can be biased, it's not just a data problem. Our model choices can also introduce bias. Models can also amplify bias. So another great paper, Moving Beyond Algorithmic Bias is a Data Problem by Sarah Hooker. Our choice of model, we can actually choose models that minimize the amount of bias in our data. If we're aware of bias in our data, there are strategies for trying to minimize the effect or the harm of that bias. But if we aren't thinking about that, if we aren't making decisions to minimize the bias, we may be making decisions that amplify it. In the stage of communicate, this is really the last stage at which we can ask, should we do this, right? So this is the last stage before a model might be deployed, before some product might be put out into the wild, where we can say, this isn't a good idea. We should not do this. Sarah Watcher-Bocher, sorry if that's not, I'm so bad at names. In her book, Technically Wrong, talks about how even when algorithms don't necessarily demonstrate bias, the final decisions are still being made by people. She gives an example of a resume algorithm that parses, thousands and thousands of resumes that come in and makes a recommendation. But the algorithm's recommendations go to a hiring committee that make the final decision and effectively put the bias right back in at the very last stage. Other issues include making decisions despite low confidence or high variance in a model, not having a sense of the potential errors in your model, of the variance, can really lead to disastrous results, or really just putting, again, arbitrary harm out into products. Another issue, mechanisms for auditing performance or reporting concerns. If you put out a data product and there's no mechanism for people to voice concerns or report errors in that product, well, then it's just out there potentially doing harm without any way for people to help you to realize that there needs to be a fix. Okay, those are some of the ways that we can go wrong at each step of the process, but I want to mention that this data science process doesn't happen in a vacuum, right? There's some context to it. The source of our data and the deployment of our models is from and into something. This target of deployment is often the source of future data, which creates a feedback loop. Again, weapons of math destruction. Cathy O'Neil talks a lot about feedback loops and how they're created. In my pre-calculus classes, we used to read chapter 3, which is the chapter on the college ranking system and the feedback loop that gets created from that. But what's the context that this data science process is happening within? It's society. Often it's society, right? So we're putting these products out into society. We're also pulling the data from society. There are just so many things that we need to keep an eye on at the very least, and so many reasons why we might want to question some of the data products that are put out. There's also, I want to mention this dispersion of responsibility. So especially in a large corporation where roles within the data science process become so specialized, it's easier and easier in those cases to just be one, one cog, right, in the system, and not have a sense of the big picture. And in that scenario, it minimizes the sense of responsibility that have, making it more likely that people will consider it not their problem if they notice something that doesn't feel right to them. So it's really important that everyone throughout this process is constantly asking questions about the ethics of the project, of the data problem that they're trying to solve. I have to wrap it up. I want to mention some recommended reading. I've already mentioned some of these, but these books are fantastic. When I was originally going to present at NCTM Atlanta, this book, W.E.B. Du Bois's Data Portraits Visualizing Black America, was going to be one of the central texts to that presentation. The visualizations out of Atlanta at the time are stunning. The history of it is really fascinating. I highly recommend that book. There's just so much I want to talk about. Okay, some more recommended reading: The Impossibility of Automating Ambiguity, Abeba Perrine. These are more academic papers, but I think they're very accessible, especially for mathematics teachers. Highly recommended. There's just so much I want to talk about. I feel like I didn't talk about anything. So please reach out via email or Twitter or whatever. In summary, the data science process is useful in my classroom It can be used as a framework for scaffolding data projects. It's helpful as an anchor reference for conceptualizing modeling with data. It provides a structure for analyzing data science applications where we can really narrow down and pinpoint where in the data science process bias or harm might be getting introduced. The process exists in context, and mathematics has consequences. Under no circumstances should you listen to Elon Musk. And modeling with data is awesome, and you should do awesome things. Again, please reach out. I hope to see you in the roundtable discussion. Email me at me. I don't know how Twitter works. Thank you so much. If you made it this far, thank you, thank you, thank you. And I hope to talk to you at the roundtable or hear from you. I really hope that this was useful for you. And thank you to NCTM. It would have been great to present at Atlanta, but I'm so happy that I got the opportunity to present at the fall virtual conference. Have a wonderful day, educators, and everyone make sure that you're taking care of yourselves.